Hi everyone, it's John. So we're going to work through week 2 worksheet this time. I crossed out the 3, it should say week 2. So it says, what is the law of conservation of mass? Right, so the law of conservation of mass states that, let me write this down. That mass cannot be created nor destroyed. So you cannot just make mass out of thin air, and you also just cannot make it disappear, right? So if you have in the context of chemistry, right, if you have a chemical reaction, you should have the same elements, right, or atoms on both sides, unless you're doing nuclear reactions. But if you're doing just normal reactions, right, if you start with 4 nitrogen atoms on one side, you should have 4 nitrogen atoms on the other side. Right now, this actually applies to other fields of science, specifically in transport phenomenon for anyone who's doing engineering or mass transfer, right? The law of conservation of mass is going to be used there. So next, the other 2 laws that you have learned about are the law of definite proportions and the law of multiple proportions. Oop, too big of an eraser. So what do these 2 say? The law of definite proportions, right? That is going to basically state that if you take water from one source, it has the same proportions of water from somewhere else, right? It's not going to be H3O, it's not going to be H10O5 or something like that, right? It's still H2O. Water from your sink, water from your toilet, water from the ocean, right? It's H2O. That is what the law of definite proportions state, right? Wherever your substance is coming from, if it is the same type of substance, water, in this case, it has the same proportions. Now, the law of multiple proportions, what that is saying is that if you have 2 different molecules, right, and they have the same elements, so like let's say carbon and oxygen, right, then the ratio of an element one to another should be in a full integer ratio. So a carbon monoxide to CO2, right? It's a 2-to-1 ratio, right? Of oxygen from carbon dioxide to carbon monoxide, right? There's twice as many oxygens as there are in carbon dioxide as there is in carbon monoxide, right? You're not going to have 1.5 oxygens. You're not going to have 3.2 more oxygens in one, right? It has to be full integer ratios or whole integer ratios. So that is it for those laws. Now, what is an isotope? So an isotope, right? When you have an isotope or different isotopes of an element contain different number of neutrons. So if you have one carbon atom that has 12, a weight of 12, actually we'll see it here, so maybe I shouldn't use carbon, but let's say if you had some sort of element, right, and it had 30 protons and 30 neutrons, right, an isotope could be 30 protons and 31 neutrons, right? The protons will always remain the same, but the neutrons can change, right? Each one is an isotope. Example maybe chlorine, right? Chlorine 35 and chlorine 34. So chlorine 35 has one more neutron than chlorine 34, okay? So we're going to move on to this table where we're going to label the atomic number, the atomic mass, the number of electrons, protons, and neutrons, right? So first thing is lithium, So lithium has an atomic number of 3. Right? So for this, you would just look at your periodic table. Right? Lithium is right here. Atomic number 3. And that's it. Right? Now the atomic number, what does that tell you? The atomic number tells you how many protons you have. So lithium also has 3 protons, right? So you want to look at the atomic number, and then that tells you how many protons your element has. All right, number of neutrons here. Actually, let's do atomic mass first. That's going to be needed. So lithium, we're going to round up the weight, right? It tells us down here to round the atomic masses to the nearest whole number. So the lithium right here, the 7, that is going to be an atomic mass of 7, right? 6.9, I rounded it up to 7. Otherwise, we're not going to get an integer number of neutrons. Okay, so next we're going to do the number of neutrons. The number of neutrons can be calculated from taking the mass and subtracting the number of protons, but why? Right, so the atomic mass, we look at 2 things. We're going to look at the number of protons and the number of neutrons. We say that protons and neutrons have a mass of 1 relative to each other, and we say that electrons have negligible mass. They're 0, basically. So we only look at the mass of the protons and neutrons, right? And if they both weigh 1 each, right, the atomic mass is just protons plus neutrons, and then I can just subtract it out. So in this case, the number of neutrons is 7 minus 3. So I should have 4 protons, right? 3 protons weighs 3, 4 neutrons weighs 4. They add up to 7. All right, so the number of electrons in this case is going to be 3. If it is an ion, in this case it's not, we're going to see one in the 3rd molecule. But if it is an ion, right, that can indicate or does indicate whether it has more electrons or a lack of electrons or more protons, essentially. So we're going to see in question 3 how ions affect it, the number of electrons. But if it is neutral, the number of electrons are equivalent to the number of protons. Okay, so now we'll go to the next one, carbon. So carbon has a atomic number of 6. Right, so has atomic number of 6, which means it has 6 protons. The atomic mass is 12 right here. Right, so that is a 12. The number of neutrons is 6. 12 minus 6, right, from the number of protons. And the number of electrons is 6, right? This is a neutral element. All right, next we have CH3COO minus. So we're not looking at the atomic number here, right? Because it's a polyatomic, right? There's multiple atoms here. Now, the way you find the number of protons is by looking at the atomic number for each of these atoms and adding them all up, right? So one carbon has 6 protons. The other carbon has 6 protons. Hydrogen has 1 proton, right? Has an atomic number of 1. Oxygen has an atomic number of 8, so it has 8 protons. So we're going to just add these all up, right? The way I'm going to do this, to condense this a little bit, I'm going to write 2 times 6, right? That's for the carbons, plus 3 times 1, that is for the hydrogens, right? Each one has 1 proton. And for the oxygens, I'm going to do 2 times 8. So you would go ahead and plug this into your calculator, right? 18 plus 3, 21 plus 16 should end up getting, oops, not 18, sorry, 12 plus 3 plus 18 should end up getting 33. 31, oops, plus 16, not 18. So you should get 31. All right, now the number of neutrons here, right? First, we have to find the atomic mass. So let's find that before finding the number of neutrons. Or we're just going to add these masses up after we round them. So hydrogen has a mass of 1, carbon has a mass of 12, oxygen has a mass of 16. So going to do the same thing here, right? The atomic mass is 2, and then times 12, right? That's for the carbons, plus 3 times 1, that is for the hydrogens, plus 2 times 16 for the oxygens. Let's go ahead and add this up. So 24 plus 3 plus 32. And you should get 59. Now, what we had to do for the neutrons, again, is just the same thing here. So 59 minus 31, and you should get 28. And then the number of electrons, right? So the number of electrons, right? First, we need to make sure or look at whether or not this is an ion, right? So if it's not an ion, if it's neutral, it's the same as the number of protons, but in this case, it is an ion. Right? We have a minus sign here. The minus sign means that you have more electrons than protons, right? Now this is a -1 charge, which means I have one more electron than protons, right? So protons are positively charged with what we would say a charge of +1 relative to electrons, which we would say is -1, right? So if this has a charge of -1, means I have one more electron than proton, which means I have 32 electrons, right? If this was a plus, instead, right, your positive ions will have one less electron than the number of protons, right? Because there's more protons, which are positive. All right, last one here. We have SO3. So SO3, we're going to do the same thing here. We did in the last one, right? So sulfur has an atomic number of 16, right? There is one of those. We have 3 oxygens, which has an atomic number of 8. You should end up getting 40, right? 16 plus 24. The atomic mass, oxygen has a mass of 16, sulfur is 32. So 1 times 32 plus 3 times 16 should end up getting 80. Right, 32 plus 48. And then the number of neutrons is 40, right? 80 minus 40. And the number of electrons is 40, right? This is not an ion. This is neutral. All right, so next we're going to do these problems with moles. So it says how many moles are present in 34 grams of copper hydroxide? So I'm going to do the horizontal multiplication that you've probably seen in class. I'm also going to write down a formula that may be helpful for some people. So the formula that you can use here, there's actually going to be a few in this section, is going to be grams is equal to moles times molar mass. Right, so you can see here that grams, moles, and molar mass are related to each other. Now, if we're trying to find how many moles are present, right, in 34 grams of copper hydroxide, so the horizontal multiplication, right, you would do this. You would do 34 grams of CuOH2, this is copper 2 hydroxide, times, now we need to use the molar mass to get the moles out, right, as we can see from over here. So the molar mass of copper hydroxide, right, what we're going to do is just add these weights up. I would recommend not rounding for these. So 63.55 plus 2 times 16 plus 1, right, for the hydroxide. Oops, missed something. And that should be 16 plus 1.008. All right, so we end up getting a molar mass of 97.566. All right, now all I have to do is, and this isn't, sorry, in grams per mole, but to be more specific here, right, this is grams of copper hydroxide, copper 2 hydroxide, per 1 mole of copper hydroxide. So for every mole of copper 2 hydroxide you have 97.566 grams. Okay, so we're going to plug this in here. I want the grams to go away, so I'm going to put my grams unit on the bottom here. The grams of copper 2 hydroxide. This is 97.566. Right, and up here we have 1 mole of copper 2 hydroxide. And then I would just go ahead and plug this in my calculator, right? The units cancel out here. And then we have 34 divided by 97.566. So we end up getting 0.35 moles. Oops, and I should put of copper 2 hydroxide. So I'm saying copper 2 hydroxide because of the charge. You'll learn about that in the next worksheet. All right, so we have this, right? I rounded to 2 sig figs because I was given 34 grams. Now, what you could also do, right, if it's helpful for anyone, is you could also, oops, not highlighter, just plug it into this formula, right? If you know grams is equal to moles times molar mass, you can say that moles is equal to grams divided by molar mass, right? That is essentially what we did, divided by the molar mass. And you can do it like that, right? If you like using formulas more, I would recommend against it. It can take more time by plugging everything into just individual formulas than just horizontally doing it all at once. But this can be helpful for, again, seeing the relationship between the two. And I'm going to write down a little kind of flow chart to show the relationships between quantities in this worksheet. Okay, so next, we're going to do the next problem. All right, the second one here says how many grams are there in 3.4 times 10 to the 24th molecules of NH3? All right, so when you're working with number of molecules or number of atoms, there's a certain number you have to use. It's going to be Avogadro's number. There it is. All right, so it's going to be right here, right? We denote that with an Na. Avogadro's number, you can think of it as, I know it just says mole inverse, but it's number of something per mole, okay? So 6.022 times 10 to the 23rd things per mole. Now, why am I saying things, right? So mole is just a unit of how much there is. It's really what it is, right? It's kind of like dozen of eggs, right? If you have a dozen of eggs, you go to the store. How many eggs do you have? 12 eggs, right? If there's a couple of things you need to do, it's 2 things, right? Half dozen is 6, so on and so forth. A mole is the same thing, right? Instead of 12 or 2, it's 6.022 times 10 to the 23rd. It's just a really big number, right? So if you have 1 mole of something, you have 6.022 times 10 to the 23rd of that thing, right? So mole, again, is just a unit of how many do you have, right? If you had 18 eggs, right, you have 1.5 dozen of eggs. So mole is very similar in that regard to the unit. Okay, so it says how many grams are there in 3.4 times 10 to the 24th molecules of NH3. So first we're going to go ahead and start with, oops, that is a laser, 3.4 times 10 to the 24th, right, molecules of NH3. Again, I like to just put everything over 1 just to line up my fraction bar. Now, another formula you can use here, again, that may help you remember the relationship, is that the number of atoms or molecules, depends on the context, is equal to the moles of whatever you have times Avogadro's number, which I'm denoting with an Na here. So I just have to continue here and keep relating each quantity to each other, right? So what I'm going to do is first go ahead and convert this number of atoms or molecules to moles, and then relate the moles to grams, right, through the molar mass. Now I'm just going to write the flow chart now. So in this little flowchart, right, the way things can be related to each other, be like this. Hoping for a box. So in this bottom left box, I'm going to put grams. This top one, I'm going to put moles. And then this bottom right one, I'm going to put number of atoms or molecules. So how do we relate these quantities is why I'm doing this flow chart, right? So from moles to grams, the way you relate those two is by using your molar mass, right? From moles to number of atoms or molecules, the way you relate those two is through Avogadro's number. Now, what about number of atoms to grams? The answer is you can't, right? You cannot directly relate these, right? So you have to go through moles from number of atoms or molecules, then go to grams, right? Same goes going the other way around, right? You can't go from grams to number of atoms or molecules. You have to go from grams to moles to number of atoms or molecules. So in this problem, right, we're going to go from molecules to moles to grams. So we're going from molecules again to moles by using Avogadro's number, right? Avogadro's number is telling us that we have 6.022 times 10 to the 23rd molecules of NH3, right? For every 1 mole of NH3 present. That goes away. All right, next here, right? So we're going to go from moles to grams. We need the molar mass of NH3, right? So we're going to add these all up. All right, so nitrogen is 14.01. Hydrogen is 1.088, 1.008. And we end up getting 7.3. I'm just going to write it up here. The molar mass is 7.034 grams per mole, right? And again, it's grams of NH3 for 1 mole of NH3. So 7.034 grams again of NH3 for every 1 mole of NH3. Right, these moles cancel out. You would go ahead and plug this into your calculator. One second. And we end up getting 39.71. And this is, sorry, grams of NH3. Right, I think the proper thing to do here would be to round this to 2 sig figs. So we would have 40 grams of NH3. Okay, so next let's go to how many molecules are there and 24 grams of iron. Again, we're going to be using this path from grams to moles, from moles to number of atoms or molecules. So I'm just going to kind of speed through this, right? It's the same thing, just in reverse as the last problem. So I'm going to start with 24 grams of iron 3 fluoride. Again, you'll learn more about the naming soon. Times, and then we want to use the molar mass, right? So iron has a molar mass of 55.85, fluorine has a mass of 19, and there's 3 of them. And should end up getting a molar mass of 112.85 grams per mole. So we go ahead and use this. This is 112.85 grams for every 1 mole. I should be more specific here. grams of iron fluoride for every 1 mole of iron fluoride, iron 3 fluoride. And then we keep going here. So now we want to go ahead and use Avogadro's number, right, to relate moles to number of molecules. So we're going to use 6.022 times 10 to the 23rd, right? Molecules, I'm just going to put molic for molecule of FeF3 for every 1 mole of FeF3. Now our final unit is in molecules of iron fluoride, iron 3 fluoride, and so let's go ahead and plug this in. All right, so this is equal to 1.2, I guess we should round to 2 sig figs, so 1.3 times 10 to the 23rd molecules of iron fluoride. Okay. So that's it for that one. Now this next one, it says how many chloride ions are in 200 grams of carbon tetrachloride. So how do you do this one? Right, so chloride ion is the Cl minus, right, or the chlorine that is attached to the carbon, essentially. So we're going to go backwards here from grams to moles to number of atoms or molecules. I'm going to relate it at the end. Now, there's 2 ways you can do this kind of at the end, from converting from carbon tetrachloride to chloride. I'm going to do it one way again. I will talk about it when I get there. So we start with 200.0 grams of carbon tetrachloride. This is over 1. We're going to use molar mass, right, to relate these. So carbon has a mass of 12.01. Chlorine has a mass of 35.45, and there's 4 of them. So this is 153.81 grams per mole. So for every 153.81 grams of carbon tetrachloride, I have 1 mole of carbon tetrachloride. Those cancel out. Right. Now, next, we're going to go from moles to number of molecules. Now, this is where things can differ. So sometimes you'll learn about it. You would change the moles to moles of carbon tetrachloride to moles of chloride. I'm going to do it a different way because I think it makes more sense conceptually to many people. However, they're both equivalent ways. So right now, what you could do, for those of you listening, is you could go ahead and convert carbon tetrachloride. For every 1 mole of carbon tetrachloride, you have 4 moles of chloride. I'm going to first convert this into number of atoms or molecules, again, because I think it's conceptually easier for people. But either way works perfectly fine. So for every 1 mole of carbon tetrachloride here, I'm going to use Avogadro's number, right, to convert this into number of molecules. So 6.022 times 10 to the 23rd molecules of carbon tetrachloride. These moles cancel out. All right, so now the last step is I have my number of atoms or molecules, but I don't want that. I want the number of chloride ions. So if you're looking at this, right? Looking at this, what is the number of chloride ions? So chlorine, right? There are 4 of them for every 1 full molecule, right? So I can say for every 1 molecule of carbon tetrachloride, right? As I said, I have 4 chlorines or 4 chloride ions. There are 4 chloride ions, right, for every single one. And this is why I think for some people it makes more sense conceptually, and you could do it from moles, right? It's going to be the same thing. But for every one molecule here, you get 4 chloride ions. All right, now you go ahead and cancel those out. So now you would just go ahead and plug this into your calculator. So 200 divided by 3.1, 2, and you should end up getting 3.1. I'm going to do 4 sig figs here. 132 times 10 to the 24th chloride ions. And that is it for this problem. Okay, so we're going to go ahead and go to the next problem here. On the back, it says, what is the empirical formula for a molecule containing 65.5% carbon, 5.5% hydrogen, and 29.0% oxygen? So these are all by weight, right? Just keep that in mind. So these are all by weight, not by mole, not by volume, it's by weight. So by mass is the more appropriate term, but these are percent by mass. So what we're going to do is consider this out of 100 grams, and I should zoom in here. All right, consider 100 grams of substance. You can use whatever you want. It's going to work out the same. In the end, it's just significantly easier out of 100 grams, right? You could use 32.356 for the whole substance, right? It's just going to be more annoying to do the math, right? So the reason I'm using 100 is these are all percents, and percents are out of 100, so it makes your life easy, right? So considering 100 grams of substance, we're going to first convert all of these into moles out of, again, 100 grams of substance. So I'm going to start up here, or else we're going to run out of room. So for carbon, right? Again, this is out of 100 grams. So if it's 65.5% carbon by mass, so I have 65.5 grams of carbon. Let's go ahead and convert this into moles. Carbon has a molecular weight or molecular mass, molar mass of 12.01. This is grams of carbon for 1 mole of carbon. All right, and then we get 65.5 divided by 12.01. And we end up getting 5.45 moles of carbon. And we're going to do this for all of them, and you'll see why at the end. So next, we're going to do hydrogen. So hydrogen, we have 5.5 grams of hydrogen. Again, this is out of 100 grams of compound times 1 mole of hydrogen, which weighs 1.008 grams. Now, you can kind of round the decimals here. It's actually better to keep a few more. So with this carbon, I'm going to just add a few more here. You don't really care about sig figs for finding out the empirical formula problems. And you'll see why at the end. We're going to divide by the smallest amount of moles. I just want to make sure that we're not getting any rounding errors. And then for hydrogen, it's 5.45 63. We'll cut it off there. And then for oxygen, right, we have 29.0 grams of oxygen. And then we have 1 gram of oxygen, right? Oxygen has a molar mass of, of 16 grams, my bad. 16 grams of oxygen for every 1 mole of oxygen. And for anyone asking is, well, why aren't you using O2, right? 32 grams for 1 mole. or diatomic oxygen, because we're considering each oxygen atom separately, right? They're bonded to different things in this, presumably in this molecule, right? It's not the diatomic gas of oxygen. So we go ahead and divide these 29.0 divided by 16, should end up getting 1.8125 moles of oxygen. So now this is not really useful, right? Just looking at it, right? What this is telling you is for every 5.4538 moles of carbon, you have 5.4563 moles of hydrogen, and you have 1.8125 moles of oxygen, right? That's not really helpful. So what we're going to do is divide by the smallest number here, right? So what I'm going to do is divide these all by 1.8125 from the oxygen. 1.8125, right? Moles of oxygen divided by 1.8125. And then this gives me 1 mole of oxygen, right? I have to do that for all of these. So 5.4563 moles of hydrogen divided by 1.8125. Give me 1 second here. And this is going to be about 3. You're going to want to start rounding here to the nearest whole number. Most of your problems should end up being within like few 100ths, right, of a whole integer. Moles of hydrogen, well, I guess all integers are technically whole, but of an integer, right, and a positive integer specifically. So if you're getting a number like 3.5, then you're going to, at the very end, have to multiply everything by 2, right? We're getting like 3.33. You're going to go ahead and multiply everything by 3. Those aren't close enough for you to just round up or down. So if you're really close, right, again, a few 100ths, then you should be okay to round. You start getting to tenths, it's a little, usually for this class, right, you should be okay, like 0.08, 0.92. Once you start getting into the 20th range, I'd question whether your math was wrong, right? You rounded too many things, or if the process was just wrong, or if you just need to multiply it. So just a helpful hint. All right, next we're going to do carbon. Now this is about the same as hydrogen. So 1.8125, right? This is going to be about 3 moles of carbon. So now that we have all these, right, what this is telling us, oops, I think my video is in the way. What this is telling us, for every 3 moles of carbon, we have 3 moles of hydrogen and 1 mole of oxygen, right? You could convert this into number of atoms, divide by the smallest number, right? You're going to get the same thing. It's just an extra step I wouldn't recommend doing. The reason I did it on the page before is it conceptually made more sense, right? But you can keep this in moles. It doesn't have to be number of atoms or molecules because they are just linked by Avogadro's number. So what this is telling us, again, 3 moles of carbon for 3 moles of hydrogen for 1 mole of oxygen. So this is going to have an empirical formula of C3H3O, right? Your empirical formula is the smallest ratio or the most simplified ratio of atoms to one another, right? So your molecular formula, as we'll see in the next one, is what is the actual ratio, right? Is it actually 4:2? Is it actually 6:3, and so on. The empirical formula is just the most simplified ratio. Okay, so like I guess some examples like C2O2, right? That may be the actual molecular formula, like how they're all bonded together and everything, but then CO would be the empirical formula. All right, next says, what is the empirical formula of a molecule containing 18.7% lithium, 16.3% carbon, and 65% oxygen? So we're just going to do the same thing here. Whoa, zoomed in a little too much, right? We're going to consider 100 grams of substance or of compound, and then just convert all of these to moles, right? So first we go ahead and start with 18.7 grams of lithium. Now lithium has a molar mass of 6.941. So 6.9, did I say 941? Yeah, 941. That's at 71. 6.941 grams of lithium for every 1 mole of lithium, right? The grams here cancel out. And then we get a number. So let me go ahead and divide this 18.7 by 6.9941. This is 2.69 moles of lithium. Should probably add a few more decimals here. Let's do 941 in moles of lithium. All right, next, we're going to go ahead and do carbon. So carbon, I should probably label these. And I'm going to do carbon right below lithium. So for carbon, right, it's 16.3%. So out of 100 grams, we have 16.3 grams of carbon. For carbon, the molar mass is 12.01 grams of carbon for 1 mole of carbon. All right, and let's see what we get. This is 1.3572 moles of carbon. All right, we can move on here. So we're going to do oxygen. So oxygen, again, out of 100 grams. Wait a second. Okay, sorry. I was checking if it added up to 100%. So this is 65.0 grams of oxygen. Then there is going to be 16 grams of oxygen for 1 mole of oxygen. That is the molar mass. So 65 divided by 16. This is equal to 4.063 or 225. Again, moles of oxygen. So what we're going to do here, and I should move all this over just so I have some more space, is we're going to divide again by the smallest number of moles. So for the lithium, right, we have 2.69. For the carbon, we have 1.36, oxygen 4.0, so carbon is the smallest. So what I'm going to do is divide everything by the carbon moles. 1.3572, right, that is equal to 1. Next, I'll do lithium. So 2.6941 moles of lithium divided by 1.3572. It should be about equal to 2. Yeah. So 2. It's about equal to 2. Again, these are moles of carbon out of space. Oh, I have more space. Moles of carbon. This is moles of lithium. Over here, I have oxygen, 0.625 moles of oxygen divided by 1.3572. And this should be about 3. Yep. So that is 3 moles of oxygen. So the empirical formula has a formula of 1 carbon. I should probably put the metal first. So let's do 2 lithiums. So Li2CO3. That is the empirical formula. That's not our answer, though. Actually, I guess it is part of it. So the first one asks for the empirical formula. The next asks for what is the molecular formula. So this is the answer to the first part. Now we're trying to find the molecular formula here. So they give us the molar mass, right? They say that the actual molar mass is 147.6 grams per mole. So the empirical formula has a molar mass of what? Let's check that. Right? We want to see how many times bigger the molecular formula is than the empirical formula. And then we're just going to essentially multiply everything by that number. So our empirical formula, we have 2 lithiums, so 6.941 times 2 plus 1 carbon, which is 12.01 plus, and then 3 times 16 for the oxygens. So we end up getting a molar mass of 73.892 grams per mole, right, for our empirical formula. Now, it tells us that the molecular formula is 147, right? So what we want to do is this. We're going to do the molecular formula, mass, molar mass divided by the empirical formula, molar mass. So 147.6 grams per mole over 73.892 grams per mole. Again, this is going to tell us how many times bigger your molecular formula is than your empirical formula, right? And you should end up getting about a whole number, right? You shouldn't end up getting like a 1.6 or something. So if you did, I would check your math and make sure everything is correct. But you should end up getting a whole number, about a whole number. So this is about, and it's like 1.99, 1.998. So this is about 2 times bigger. So what this tells us is that my molecular formula is 2 times the empirical formula. Right, so all I have to do here is take my empirical formula and multiply everything by 2. So the molecular formula is going to be Li4C2O6. And that is your final answer. Okay. So we're going to move on to the next question here. We have copper 2 hydroxide. So what is the percent copper, oxygen, and hydrogen? So you're just going the other way around here, right? So you're taking the molar mass of copper in this compound, dividing it by the total molar mass, and then you're doing this for oxygen and hydrogen. So, right, this copper hydroxide, I'm just going to look on our last page here. So this copper hydroxide had a molar mass of 97.566, copper 2 hydroxide. 97 point, I forgot, 566 grams per mole. Okay, so now all we have to do is, again, take the individual components and divide them by the total molar mass, and then multiply by 100%, right? So a little bit out of room here. So copper is 63.55 right here. So 63.55 grams per mole divided by 97.566 grams per mole times 100%, right? That's always what you do to convert into a percent. And we're going to get some number here. So 63.55 over 97.566. You end up getting 65.14% copper. Right, and then we would have to do it for all of these, right? So oxygen, there's 2 of them. I'm going to stop putting the grams per mole just so I don't have to write everything. I'll just write it in. 32 grams per mole over 97.566 grams per mole times 100%. Again, you're taking the ratio of these molar masses, 32 over 97.566. And you end up getting 32.80% oxygen. Next is going to be percent hydrogen, and you have 2 of those. So it's 1.008 times 2. So 2.016 grams per mole over 97.566. I'm actually going to move it over here. I don't want to go into the next question. Times 100%. And you should end up getting 2.07% hydrogen. Okay, next we have nickel 3 sulfate. So we're going to do the same thing here. So the molar mass of nickel 3 sulfate, right, we're just going to add everything up. Ni2SO4 3. So the nickel has a weight of 58.70. Now we have 3 sulfates. So I'm going to multiply the whole weight of sulfate by 3. So 3 times sulfur is 32.06, right? Oxygen, there's 4 of them. So 4 times 16 in each of those sulfates. You should end up getting a molar mass of 346. Oops, I forgot to do 2 nickels. All right, so 405.58 grams per mole should be what you get for the molar mass. All right, so what we're going to do next, again, is just divide all of these. So nickel, 58.7 times 2 divided by 405.58 times 100%. I'm not going to write these all down just for the sake of time in this video. I think it's going to be about an hour already. So you should end up getting 28.95% for nickel, right? I did 100 or 58.7 times 2 divided by 405.5 times 100%. Right, for sulfur, 32.06. There's 3 of them divided by 405.5 times 100%. This ends up being 23.72%. And then lastly, for the oxygen, you get 16 times 4 times 3, right? There's 12 oxygens in total, divided by 405.58 times 100. So you should end up getting 47.34% oxygen. And that's it for this one. Again, it was the same process as the last one. If you're having trouble, I'd recommend just writing it out. It's going to be the same process. All right, next is molecular formula. It says a compound with an empirical formula of C2H8N and a molar mass of 46 grams per mole. So first, let's find the empirical formula mass. The molar mass of this empirical formula, right? 2 carbons. So 2 times 12.01 plus 8 times 1.008 plus 1 times 14.0 0.01. So we're just going to go ahead and add these up. All right, and then we're going to go ahead and take our molecular formula and divide it by this, which you'll see we don't actually need to. We end up getting 46.094 grams per mole. Now that is the same, pretty much the same, right, with rounding. So these two are the same, right? You can go ahead and divide them, right? 46 over 46.094 if you want to be super thorough. And you're going to get 1, right? So these aren't a 1-to-1 ratio. So your molecular formula is your empirical formula, right? They may not be the same, but they also can be the same. I think that was worded a bit weirdly. So right, they can be the same, but they may not be the same. So it just depends on what the molecular weight is, or molar mass of the actual compound. So in this case, the molecular formula is the empirical formula, which is C2H8N. All right, next it says a compound with an empirical formula of carbon, fluorine, bromine, and oxygen, and a molar mass of 254.7 grams per mole. So again, so the molar mass, let's find the empirical formula, molar mass. I'm just going to add these all to my calculator. So we have 1 carbon, 1 fluorine, 1 bromine, which is 79.9, and 1 oxygen, which is 16. So we should end up getting 126.91 grams per mole. Now I'm going to take my molecular formula, 254.7 grams per mole, and I'm going to divide that by 126.91 grams per mole. 254.7 divided by 126.91, right? We end up getting about 2. Just want to give you the decimals at the end. It's 2.006. You should be very, very close. This is within thousandths of the integer. So this is about 2. Right. Now that means that the empirical formula is about half of the molecular formula. So the molecular formula is C2F2Br2O2, right? We're just taking everything and multiplying it by 2. Okay. All right. I should have squared that. This next one says, how many carbon atoms are in morphine, right? So this is type of drawing that you'll see a lot in organic chemistry. So the carbons are going to be the vertexes of each of these shapes. So right over here, we have a carbon. Over here, we have a carbon. Over here, 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 and here. Most of these are not labeled with carbon, but they are carbon. There's some naming rules that you'll learn once you get to organic chemistry. But if it's one of these vertexes and they're not labeled an atom, it's carbon, right? If it is labeled carbon, it's also carbon. So we're just going to count here, right? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now it's not 15, right? You have these kind of weird wedges in the middle right here. These vertices are also carbons. So 15, 16, and 17. So the answer is going to be 17 carbons, right? Those wedges mean that they're pointing at you from the paper. So when they're pointing out, it's like that is a wedge. That's how we draw it. A dash, if you see those, actually there's one right here. Dash is like going into the page. So you have a flat page, right? It's pointing into it, away from you spatially. Okay, so last but not least, we're going over averaging the atomic mass. Now, for anyone who's taken the SAT or ACT or some basic probability, if you haven't, that's totally okay. But these will be familiar for those that have taken those problems. So it says we have rubidium has two common isotopes, right? You have 85 and 87. Those are the masses. The abundance of rubidium 85 is 72.2%, and the abundance of rubidium 87 is 27.8%. What is the average atomic mass of rubidium? So what you're going to do here is take a weighted sum, right? So you can see here that clearly there's more rubidium 85 than rubidium 87. So how do you show that? Right, you're going to take the molar mass, of the first rubidium, or in this case, they say atomic mass. So 85, and I'm going to multiply that by the decimal form of what percent abundance you have. Now, for those of you who have taken, again, SAT, ACT, probability stuff, this is similar to doing probability questions, right? So if you had a probability question that said, you have a hat full of numbers, and half of those numbers are 6 and the other half are 4, what is the most probable outcome, or what is the or what the technical term is, right? But what's the expected outcome, right? In terms of probability, the expected outcome ends up being 5. You can't actually pull a 5, right? There's only 6s and 4s, right? But you're taking the weighted sum of each number and its probability and then adding them together, right? So half of 6, you get 3, plus half of 4, which is 2. 3 plus 2 is 5. There's not actually 5, right? Just like in here, no atom is going to actually weigh like 86.35, right? They're going to be pretty much 86, right? 85, 87. They're not going to be half a weight, right? So this is what it is, right? So again, it's a very, very similar type of problem, if not the same. So next we're going to go ahead and just add the other one, right? This is going to be the atomic mass, 87, times the decimal form of the percent, 0.278. You add these up, again, this weighted sum. And you end up getting 85.556. Right, so that is the atomic mass of rubidium. You could write an AMU, but that is it. Again, no rubidium is actually 85.556. Either from this problem, it's either 85 or 87, at least for the common isotopes. Or maybe there's 86, 84, 88, I don't know. But they're going to be whole numbers. All right, next it says titanium has 5 common isotopes. So you have titanium 46, 47, 48, 49, and 50. All right, what is the average atomic mass of titanium? We're just going to do the same thing here. It's more of them, but it's exactly the same. So what we're going to do is just take each atomic mass and multiply it by its percent form in decimal. Multiply by the percent as in decimal form. Right now, this 8%, right? This is a 0.08. Don't make a mistake. It's not 80%, right? Do not put 0.8. You will get this whole thing wrong. Right? That is a common mistake when converting with these percents. So similarly, again, with 7.8%, it's 0.078, not 0.78. That's 78%. Then we're going to keep going here. So this is 47, 48 times 0.734 plus 49 times 0.055 plus 50 times 0.053. All right, and then you're just going to add these all up, right? You would just plug this into your calculator. Let me do that. And you should end up getting 47.923 for the average atomic mass. All right, last one. It says, which one is a halogen, right? The halogens are just in the second to last column here. Fluorine, bromine, chlorine, and iodine specifically. So fluorine, that's your answer. All right, rubidium, if we're to look for that, rubidium is a group 1 element. This is an alkali metal, not alkaline earth metal. Don't mix them up. All right, alkaline earth metal is that second column. Sulfur is over here, right below oxygen. Calcium is an alkaline earth metal, right in group 2. And then krypton is a noble gas in that last column. All right, so that is it for this worksheet. I hope that helps. And I will see you again in the next worksheet.